Welcome back to my Intel 8088 breadboard computer series. This is the 6th video in which we are going to add 2 more chips to our computer. But before that, let's continue what we started in the last video. We ran our computer in the single step mode and saw its state on the LCD, but there was no way of stepping through any further as we didn't have means to restart the program. We need a button to be able to press it when we are done with the current state of the CPU and let it know it may restart executing our code. Do you remember the video where we simulated the interrupt controller to see how 8086 handles interrupt requests? We then used the 74244 chip, the 8-bit tri-state buffer, which was asserting its outputs every time it received the int A signal from the processor. After the test, I had disconnected its output enable pins from the int A and left it on the breadboard permanently inactive. Today, we can reuse it as an I/O device, which, when read, would simply return its input states set by the buttons we're going to connect. The idea is shown on this schematic. This allows us to use 8 buttons altogether, but today we're going to need only 2. The OR gate you see in this contraption is required to enable the buffer's outputs only when the correct I/O address is chosen, and also when the CPU attempts to read it. There's no point of writing data to the buttons, is there? So this OR gate outputs 0 only when both the chip select signal coming from our address decoder and the RD CPU's pin are low. In our particular case, we already have the chip containing NOR gates available on our breadboard, which we used for driving the LCD, so we will build this OR gate using 2 NOR gates like that. So, as I mentioned, this is our 74244 8-bit buffer. Currently, its output enable pins 1 and 19 are just shorted to the VCC, so they are permanently disabled. But now I'm going to use them as the I/O device, which just reads the state of the buttons which we're going to add. We need 2 buttons, as I mentioned. I think of putting them just over here next to the NOR gates and our I/O address decoder. Also, I'm going to use this RC filter to each of the buttons to filter out any contact bounce in this push buttons, and then I'm going to connect them to the 2 bits of the 244. Now it's time to connect both of the buttons to our input pins of the 74244. I just need to, that's our reset wire. Pin number 17 and pin number 15. These are 2 least significant bits we connected via those buffers to the data bus. I think we're done with the buttons. Just to explain why the 2. One it will step through the program instruction by instruction. The other one, I thought it would be useful when we want to stop single stepping through the program and just run it with full speed without setting the TF flag. So that's what the second button will do in our code. Now we need to drive the output enable pin of the 244, which, as I mentioned, is currently held at 1, which is inactive, means that it will never be asserting any signals from its outputs. They are in high impedance level if the output enable is 1. Now we need to drive it from our OR gate, which will create from available gates in the 7402, this one actually, this one 7402. We used only 1 gate, 1 NOR gate previously to drive one of the signals of our LCD. Now we will use the other 2, maybe here at the bottom, to create an OR gate, which would then drive our signal, output enable signal of the 244. So I'm going to use these 2. So output 1 is the output of our read signal to the 244, which goes down to pin 1. And this gate, first gate in this IC is just an inverter, so I need to connect both inputs together, and those inputs need to be driven from pin number 4, which is output of the other gate. And now inputs 5 and 6 we need to drive from. One is from the IO device address decoder, which is simple, it's just next to it, and the other one needs to be driven from the RD signal of our CPU. Okay, it looks like I've done all the connections. This is our RD signal, which goes to the pin 5, one of the inputs of one of the NOR gates. Pin 6 is connected to the next available chip enable kind of decoded address in the IO space, which is active for 10 hex, well, 1x hex really. And so that both signals, both zeros, both active signals, the chip enable for the IO device and the RD signal will make the NOR gate to issue high level and its output, and then we negate it to get 0, and the 0 will only be active when both signals are active, and this will activate our 8-bit buffer here 244, which will then just present this state of these two buttons. Other 6 lines are hardwired to some states which we used in the previous video, which we can then read in our software. Okay, let's try that. I just found that I made a mistake here. This wire should go here, otherwise it wouldn't work at all. Now look at the changes I've made to the code to read the state of the buttons and allow us to step through the program on each button press. So the first change I would like to show you is within our interrupt handler. Remember, we had this infinite loop in the last video, because after the first single step interrupt was raised, we wanted to pause the program to see what was on the LCD. We can actually remove now this infinite loop. I added the code to wait for the user to press one of the two our new buttons. I created this new function button wait for press, which I will show you in a second. So it waits until one of the two buttons has been pressed, and then it carries on with the interrupt. And based on if the button which would step through to the next instruction is pressed, the TF trap flag is either set or reset on the stack. We use this BP +6, which is the same offset as here, where we copy the flags register from the stack. That's where it's saved by the processor when it starts handling the interrupt just before calling our handler. So if the step button is pressed, we will set the trap flag again. And if it's not, it means that we want to carry on with our program without stepping through, and we clear the trap flag on the stack. And then we exit the interrupt handler. You've seen those definitions, button debug step and button debug run. These are added into our system definition include file. I've defined first the address of our IO device, which will activate our 74244 chip, and then 8 buttons, which of I defined with proper names, just 2 of them. And as you can see, the definition is just 1 bit for each button connected to our 74244. Let's now go to the new file I created, buttons.asm, which contains currently only one function, button wait for press, the one we used in the interrupt handler. What it does is to check the periodically, with some delay, our 74244. If any of the buttons chosen by this mask is pressed, then the function leaves, setting the appropriate bit in the return value to the button which was pressed. And finally, our init procedure, which is run straight after reset. I removed the old test code, which was setting all the registers to some known values. We currently know that our single step works. I just added the code which reads just once, reads the buttons register, and currently when the button to step through the program is not pressed during reset, the program will set the trap flag, but the intention afterwards is that only when you press the step button when you reset our computer, it would go into single step mode. So that's what this code does currently. Our main function is empty, so I just kept it commented out and added our Fibonacci sequence program from our previous video just to test our buttons. That's the theory. Now let's test it in practice. Okay, let's power it up. As you can see on screen here, this is our first program we ever ran on this machine in our second video of the series, which is the program generating numbers from the Fibonacci sequence. The only modification I made in this program is to use the whole 16-bit registers this time. So we generate Fibonacci sequence in the AX or 16-bit, and the BX is the helper register which we use along. Right, so at IP of 46, offset 46 in the code, we've got the add BX AX. So that's going to be the next instruction executed on our CPU. As soon as I press the step button, and the IP should move to 48 to the exchange BXAX instruction. Let's try that. Okay, looks like our step button actually works. 48 IP equals 48. Now BX is modified to the value of 1. That's the effect of add BXAX. Previously we had 0 in the BX register. We added AX 1 to 0, resulting in 1. Next step should execute the exchange BXAX instruction, which actually doesn't do much on the screen because both registers have currently the same value, but we should be able to see the IP changing to point the next instruction, which is jump at offset 49. And there you go, as I said. So no changes to AX or BX, but we moved on to the jump instruction, which with the next press of this button should jump back to offset 46. Let's try that. Okay, it looks very good. Now we're going back to the add instructions, which adds AX to BX. So this one should be added to this one, resulting in BX equal to 2. And that's what happened. Then now we exchange both registers, jump back, add, exchange. So that's another Fibonacci sequence number 3. Let's go a few loops. Now we've got 5. Do you remember how many clocks we had to generate manually for the CPU to move over this loop? Now it's just 3 steps because it's just 3 instructions in a loop. Okay, so we've got 8 in the accumulator. Next is D, which is 13. 1, 5, which is 21. 2, 2, which is 34. 3, 7, which is 55, I guess. 5, 9, which is 89. 9, 0, which is 144, is it? I think so. Next, E9, you guess what's the number in decimal. In the very first video, I set my goal for this series to write and play a video game on our computer. In order to do that, we need a time base, a regular clock which would set the pace of the game. It is usually called a system tick in operating systems. That's why we need a programmable counter, which I have planned to add to the breadboards today. The counter will raise a periodic interrupt and thus create the system tick. But to handle the interrupt requests properly, we need the PIC, the Programmable Interrupt Controller. It was fun simulating PIC's response to the CPU in a previous video, but today we need the real chip, the 8259. Now let me explain what has happened on our breadboards. This is our 8259. These are the 8 bits of the data bus, which don't lead directly to the 8259. They break here, and I did it in anticipation for building in a yet new chip on our breadboard. We'll get to that in a few minutes, but now all you need to know is that these data bus, these lines of the data bus go to our 8259 here. Also, I did a similar thing for these two yellow wires. These are inter from the CPU, so interrupt requests signal, and the interrupt acknowledge signal. I broke them here for a different reason, honestly. I just didn't have long enough wires when I was building it a few minutes ago. I'll replace them in a minute when I will make more changes to this breadboard. I also needed the A0, the least significant bit of the address bus here, because the 8559 contains 2 registers. Similarly to our LCD, we need to tell between the two. From below, I just extended this A0 going to LCD, from the LCD to our 8259. Those little short green wires ground 7 of 8 of the interrupt request lines of the 8259 because it recognizes 8 different interrupt sources. The 8th one, I just ended up with this wire, which I can switch between the ground and the VCC to raise an interrupt, just to test if I built the chip correctly in our computer. This is our computer's current schematic. The PIC requires configuring it by sending a few control words to its I/O ports. Let's have a look at the code I've written to do that. I'm going to start almost as usual from our system.def file. As you can see, we have now definitions for our registers of the PIC 8259. You might notice that there are many names, but only 2 values repeat between them. That's because there are really 2 registers, but depending on how and when you use them, they have different meanings. So, for example, these first 2 are used in the initialization of our PIC. When you send control words to define how this chip will behave, and the rest are used during the normal use. Some of them are read-only, some of them are read and write. The last value is the first interrupt. It would be configured for the PIC to raise interrupts. As you might know, PIC has 8 interrupt request pins, so it can handle 8 interrupts, and during initialization you can configure from which vector number the PIC would start raising the interrupts, and it raises 8 consecutive numbers starting with the value configured. So we used number 8, so the interrupt request number 0 would raise interrupt number 8, the next line, number 1, would raise interrupt number 9, and so on. These values are used in our new file, pic8259, where I defined 3 functions. The first one, picinit, as you might have guessed, it initializes the PIC. It does so by sending those mentioned control words to both registers into the PIC. And these two particular lines disable initially all the interrupt lines. The IMR stands for interrupt mask register, and each one disables the pin in the PIC. The other two functions, PIC disable interrupt and PIC enable interrupt, do what you may expect. So they set or clear the chosen bit in our IMR register using this parameter, which holds the number of the line to be disabled or enabled. So that's it here. Now let's go to this invect ASM function. First of all, I created a new function called setIntVector, which sets the vector of a new interrupt we want to configure in our interrupt vector table. So it takes two parameters, number of the interrupt we want to set and the pointer to the interrupt handler. It modifies the table at the very bottom of the RAM, where the interrupt vector table sits. And because of the name of this function, I renamed the other function which was here originally. It was called setIntVectors, which was really initializing the vectors based on the on this table at the bottom. So I just simply renamed it to initInVectors just to avoid confusion between the two. If you let me, I will go back to the PIC file. I forgot to mention about those instructions at the beginning and of each of the functions. The pushf and CLI, it saves the flags register and then clears the interrupt flag, so it effectively disables the interrupts during executing these functions and then just pops a flags register back to its original state. That's just to avoid any problems with interrupts when we modify PIC configuration. And finally, our initialization code, at the bottom of which I added this IR0 int handler. That's our test interrupt handler, which would be called when we raise an interrupt using our PIC. That's nothing but NOP, and PIC AOI command is not a CPU instruction. It's a macro which you can define in NASM and then call it. The macro is a new file which I created here. So what the macro does is to let the PIC know that we've handled current interrupt, and it may go on to raise new interrupts if there are some requested. That's what should appear at the end of each interrupt which was sourced by the PIC. And that's what we're doing here just before the IRET instruction. And now lastly, the changes I made to the initialization code itself. I added PIC init, call to PIC init, which as you saw initializes the PIC by sending those control words. Then we set the vector of the interrupt which we expect to raise using PIC to our handler here, and finally we enable accepting those requests on the IR0 pin of the PIC by calling our new PIC enable interrupt function in the PIC8259 ASM file. The rest of the code didn't change. I still have this Fibonacci sequence to be executed while I'll try to raise the interrupt using the PIC. Everything looks like it's in place for testing. Let's try that. So our CPU is at the beginning of our Fibonacci sequence program, which we tested previously. The IP is 5D, so as you can see here in this listing, it is our XOR BXBX, and it carries on in the loop, generating us Fibonacci sequence, as you can see. But now, if I switch this orange wire to VCC it should raise an interrupt coming from 8259, which handler is just below the Fibonacci program at offset 0066. Let's try to do that. And look at that, straight away. I can lower the interrupt request signal back down to 0, but our CPU already started executing our interrupt handler. So the 66 IP is the NOP instruction. Then it goes to let the 8259 know that it's done with this interrupt, and 8259 can then listen and wait for more requests. So 6A, that's our out to the port of 8259, pop AX and IRET. After this instruction, we should get our CPU back to our Fibonacci sequence program. 5F, yes, we're adding AX to BX. Oh, we already got into quite a big number. And that's what's happening here. So it looks like our 8259 works perfectly well. It looks like we are ready to add the timer, the 8254. First, let me replace those interrupt wires from the CPU to 8259. So there it is, our 8254 timer. I'm going to put it right here. That's why I left those data bus wires broken here, because they perfectly match the first eighth of pins of the 8254. And before I carry on, I think I need to remove the LCD temporarily, because now I have access to the A0 address line. And I also need to put a wire from the A1 to the timer. As I mentioned before, it requires 2 address lines. Okay, I think I'm done building in the 8254. As I previously said, the first 8 pins of this timer is the data bus. Then we've got series of 3 timers: clock in, gate, signal, and out. We set all gates to logical 1. And saying all gates, yes, I did for that one as well. So all 3 gates are set to 1, which means that the clocks are enabled, timers are enabled, just in case we want to use more than one. Currently we're using 1 timer 0, which output is connected to the interrupt request of our 8259. So hopefully, when the software enables the timer, it should raise periodic interrupt. First, let's test if the computer as a whole still works. Oh, one thing worth mentioning: the blue long wire is our peripheral clock signal from the 8284, which is half the value of the main CPU clock. So currently our crystal is 6 MHz. Divided by 3 gives us 2 MHz main clock and 1 MHz this peripheral clock, which goes up to all of the clock inputs of the 8254. Okay, let's try if our computer works currently with the current old program. Looks like it does. And of course, the wire raising the interrupt is not here. It's now connected permanently to the 8254 counter zeros output. So there is no interrupts, but I didn't break anything, at least building in this timer. So it all looks good. This is how the computer looks like now. And of course, with the new hardware comes new software. And again, we're starting with our system definition include file. As you can see, I added new definitions for our PIT or PIT, Programmable Interval Timer. This chip includes 3 identical counters. Each of them has its own register. And the 4th one, all 4 registers require 2 address lines, as you saw when I was building it on our breadboard. We needed to join both A0 and A1 lines. So the 4th register is the control register, which defines how we access and what we do by accessing the other 3 registers. Then I defined the vector number using the previously defined pick_int_vec number here. Because we're going to use the same line as just a few minutes ago, this is going to be the same interrupt number. Also, I defined the frequency of our system tick. I decided to have 100 interrupts per second, and that is used in the code I would like to show you now. That's the new file, which contains all the functions needed for our timers. And the definition I just showed you is used in here to calculate how many steps the counter needs to count before raising a new interrupt. That's based on our system peripheral clock generated by 8284. This calculates and then configures our counter number 0 in 8254, and then similarly to what we did in our previous test, we set the interrupt handler address in the interrupt vector table, and we enable the line in the pick. The interrupt handler is down here. What I did here is to define a double word, which is 32-bit value, which I called systic count. It's a variable, as you can see in the data section, which will count our system ticks. What our interrupt handler does is to increment the tick count. It does it in 2 steps because we're using 16-bit processor, so we can increment only 16-bit values. Our registers are 16-bit values, but as you can see, I didn't even need to use any registers, because 8086 enables operating on the memory directly, not like RISC processors. So what we do here is we first increment the value in the lower part of the 32-bit value, and using the 0 flag, if the result of incrementing is not 0, so there was no carryover, we just jump over. If there was 0, it means there was a carryover to the older or higher part of the 32-bit value. So what this code does is just increment the whole 32-bit value each time our timer raises the interrupt. And the usual macro to finish with the interrupt and let the pick know that it can request another interrupt if there is one. There is one more function here called getSysTicks, which, as you may expect, just returns the 32-bit value which currently the variable down here holds. And we did the same trick to disable the interrupt just for the moment the function reads those data, because the interrupt could be raised in between these 2 instructions. So we first read the lower part, then the interrupt may be raised in this moment, and modify the values, and we could get the both halves wrong. So what we did here is to disable the interrupt, read both values, and re-enable if it was enabled after that. And as you can see, and if you remember the previous video on calling conventions, if we have a 32-bit value to return from a function, the lower part is in AX and the higher part is in the DX. That's exactly what we do in this function. Let's move to the initialization code. I added the pit init function to initialize our timers. I removed the temporary condition which defined that if you don't press the step button on the reset, it would go to the single step mode. Now we start to use our computer, so by default, when you don't press the step button, it would just run the program normally, and only when we press step while resetting, it would set the trap flag on. And we reinstantiated the call to our main function, which contains the code, our test code, which effectively in the loop reads the systic here, and when it changes by 100, which is equal to 1 second now, it will display our systic counter divided by 100 on the LCD, more or less in the middle of the screen. Why 100? Remember, there are 100 ticks per second, so we should have a number of seconds counted on the LCD since we restarted our computer. As you can see, our timer is working as expected. In the last video, we made no changes on the breadboards, as the whole video was mainly focused on the theory and programming side of things. Today, in a much shorter time, we already added 2 chips to our computer and programmed them. This could be as well the end of this part, but before we wrap it up, I would like us to have another look at the first test we did today, where we ran the Fibonacci sequence program step by step, but this time from a different angle. Now, I'd like us to focus on the flags register displayed on our LCD after every step. First, let's have a look at the control flags. The IF is set as I used the STI instruction, and obviously the TF, the trap flag, is also set. By the way, there is one thing I haven't mentioned but becomes quite obvious when you think about it. When the processor calls the single-step interrupt handler straight after saving the flags register on the stack, it also clears the TF flag, so the handler can be executed normally. If it didn't do that, the handler would never pass the first instruction, which would raise the interrupt again and again in an infinite recurrence. At the end of the handler, the IRET instruction resets all flags, including the TF one, to their pre-interrupt states. Remember that what we see here is the state at the moment the interrupt is raised, so the TF is set here. Let's move on to some of the status flags. We can see the ZF and the PF both set, and the rest is cleared. They reflect the result of the last instruction executed, which was XOR BX BX. Since it zeroed out the BX, by definition its result was 0, hence the ZF flag set. Also, since 0 has an even number bits set, namely 0, the parity flag is also set. Number 0 is non-negative, so the sign flag is not set. Also, the last instruction was not an arithmetic operation, so neither the OF, AF nor CF are set. In the next step, we added the AX to the BX, so the result was 1, and since there was no carryover or overflow, the OF, AF and CF stayed cleared. The parity flag got cleared as well, as number 1 contains an odd number of bits set, and obviously 1 is not equal to 0, so the ZF is also reset. The next instruction, exchange BX AX, modifies no flags as well as the following jump. If we moved a few iterations forward, we could see that the AX contains 0D or 13, and the BX holds the value of 8. The next instruction, which adds the AX to the BX, results in number 15 hex, or 21 decimal, which sets the AF flag. Just to remind you, the AF signals that there was a carryover between the half bytes, which in hexadecimal are represented by a single digit. In other words, the second digit to the right in the BX turned from 0 to 1. The AF is used very rarely and only by a group of special instructions which form the BCD, or binary coded decimal numbers. There are no conditional jump instructions which would test this flag. That's it for today. Thank you for watching, and please don't forget to like this video and subscribe if you haven't done it yet. Next time we will get even closer to achieve my goal for this series, so I hope to see you there.